So, very pleased today to welcome Will Rushworth, and he's going to talk about doubled Khovanov homology.
Okay, thanks very much for asking me to speak. I'm going to see if I have permission to share my screen.
You should
Great.
be.
Okay,
If not, I
perfect.
can give you permission.
I hope everyone can see that.
Not so. Oh, yeah. Yeah.
Okay, great. Thanks very much to Roger and Lou for asking me to speak. Roger and Lou asked me to give something expository about doubled Khovanov homology. So what is doubled Khovanov homology? It's an extension of Khovanov homology to virtual links. So I'll start by describing these two things. They're both huge topics, so I'll just say enough that I can move on to the third topic, which is doubled Khovanov homology. And then, time permitting, I'll see if I can talk about some applications and extensions of this construction. So let's start with Khovanov homology. It was introduced by, no prizes for guessing, Khovanov in 1999. And as I say, there's a lot to say about it, but I'll just stick to a whistle-stop tour. It's an invariant of oriented links in the three-sphere. And given such a link, we denote by KHL the Khovanov homology of the link, and it's a finitely generated and bi-graded abelian group. And perhaps most famously, it categorifies the Jones polynomial in the sense that this group is bi-graded, and we can do something called the graded Euler characteristic and recover the Jones polynomial of the link. But it's strictly stronger than the Jones polynomial. It separates some links that the Jones polynomial fails to do. But perhaps more importantly, or the more important upgrade over the Jones polynomial that Khovanov homology enjoys is functoriality with respect to cobordisms, in the sense that given a cobordism between two links, then the Khovanov package gives you a map between these two, the groups assigned to the links. And I might say some more about this towards the end, depending on the time. I was 9 years old when Khovanov homology was first hit the archive. So I was more interested in dinosaurs and Lego and stuff. But I'm reliably informed that when it did first arrive on the scene, the fact that it contained geometric and topological information about the links was highly about the argument link rather was highly unexpected, and that's because the definition. Wow, that was. I think that's some feedback somewhere.
Can everybody please mute, except the speaker, of course?
Okay, that sounds better. Okay, I think it's gone. So why is it unexpected that Khovanov homology contains geometric or topological information? It's because the definition is purely combinatorial. Given a link diagram, there's an algorithm a combinatorial algorithm that you can use to obtain this group. But nevertheless, Khovanov homology does contain much interesting geometric topological information, perhaps most famously about the slice genus, the Rasmussen invariant, lots of concordance information, but it also contains information about surgeries on links, about fiber surfaces for fibered links, and the list goes on. So one way to begin to explain why Khovanov homology contains this information, one possible explanation, is because it's related via various spectral sequences to a range of gauge theoretic invariants, Floer homologies of links and manifolds. And these Floer homologies are naturally and manifestly geometric in nature. And so the fact that Khovanov homology is related via spectral sequences to them goes a long way to explaining or justifying perhaps why it contains this information. And actually, in a rather concrete sense, one could say that Khovanov homology is some sort of master invariant, in the sense that these spectral sequences start at Khovanov homology and abut to a gauge theoretic invariant. So in a very concrete way, Khovanov homology can be thought of as containing these other gauge theoretic invariants. And this bullet point cloaks a huge amount of work. This idea of relating Khovanov things to Floer things via spectral sequences is a very large topic by now. And I'll just flag up some very important recent work, that sort of most recent tip of the iceberg. There's a paper by Kotelski, Watson, and Zubovius that fits into this framework, as does recent work of Alice Shahi and Dowlin and Oshvat Sabo. So this is very much still at the cutting edge of understanding of our understanding of Khovanov homology. But despite a huge body of work and much deep work, it would still be fair to say that we don't really have a satisfactory or complete understanding of where Khovanov homology comes from. In other words, you could say we don't really know to a satisfactory degree what the invariant is. Why does this simply defined invariant contain so much interesting stuff? And so in light of that, the problem of extending Khovanov homology from links in the three sphere to links in other three manifolds becomes a desirable problem to answer for at least two reasons. Firstly, it's because it's reasonable to expect that such an extension would be useful in the study of links in other three manifolds, i.e., if you wanted to do knot theory in a wider class of three manifolds, the fact that Khovanov homology is so useful when studying links in S3 makes it plausible to expect that any such extension would be useful for knot theory in wider classes of three manifolds. But secondly, in light of the sort of mysterious origins of Khovanov homology and the fact that we don't really have a satisfactory answer of what it is, an extension of Khovanov homology to a wider class of three manifolds would also be plausible, or it would also be plausible to expect that could shed light on the nature of the Khovanov construction itself. There's been slightly less work on this problem when compared to the nature of relating Khovanov to Floer theories, but there is some very important work, which I should flag up the slightly older paper of Asiada, Shatitsky, and Sikora, where they extend Khovanov homology to I bundles over surfaces, which is very related to...
Excuse me, Will, can I ask everybody to mute themselves, please? Sorry, Will, carry on.
No problem. Yeah, and so this APS paper is quite relevant to what I'm going to talk about today. Maybe I'll mention it towards the end. And then there's even more work of Willis, where he constructs a Khovanov homology for links in S1 cross S2 and connect sums of S1 cross S2. And then finally, there's a very wide-ranging, quite large scope paper, quite recent, of Morrison, Walker, and Weidrich, where they use the Khovanov construction to define four manifold invariants. And so in light of this problem of extending Khovanov homology to wider classes of three manifolds, what I'm going to talk about today is an extension of Khovanov homology that could perhaps represent a step along a path towards Khovanov homology for wider classes of three manifolds. Now, I put in my abstract that I wasn't going to assume familiarity with Khovanov homologies, and I'm not. So I'm going to give a definition via an example. As I said at the beginning, the topic is a huge topic, and Khovanov homology can do many things. And so I'm only going to focus on the parts of the construction that are relevant for my talk. Yeah, the caveat being that this is going to be quite a whistle stop overlook. But the idea is, as with any homology theory in the Khovanov tradition, we take an oriented link diagram, and then we use that diagram to produce a chain complex. And this is done in a purely combinatorial way. But this chain complex depends on the link diagram. Applying a Reidemeister move will change the complex, but if you've done it right and you've set everything up correctly, the homology of this chain complex will actually be a link invariant. So an invariant of the link represented by the diagram. And so this is the general idea. How do we do this first step from a link diagram to a chain complex? Well, the only thing really that we have in a link diagram are the crossings. We just have a bunch of arcs connecting some crossings. And at these crossings, we can resolve them in one of two ways. We can come from the underpass and turn right and replace the crossing with this tangle. We call this the 0 resolution. Or we can come from the crossing and turn left and replace the crossing with this resolution. We declare it to be the 1 resolution. And so this is the construction we're going to use to produce a chain complex. I'm going to apply it to this very simple diagram. It's a very boring one, but it's chosen for a purpose. And it has 2 crossings. So a string of 0s and 1s of length 2, i.e. an element of this set here, will define a full resolution of this diagram, i.e. it will dictate to me how to resolve all of the crossings of the diagram. If I do that and resolve all of the crossings, what I'll be left with is simply a collection of disjoint circles in the plane. I started with a link diagram. The only points at which a link diagram fails to be an embedding is of course the crossings. And I'm simply removing all of them, so I have to end up with an embedded collection of circles. And I get one of them for every element of this cube. And here I've drawn all of the smoothings I get when applying the process to this diagram. And I've arranged them from left to right by increasing number of increasing number of 1s. And I've placed them neatly on the vertices of the cube. So this is going to be the starting point, and a chain complex will magically appear. The next step is to take these collections of circles and replace them with algebraic objects. And what I'm going to do is I'm going to pick a certain module. It's always going to be denoted by calligraphic A. And every time I see a circle, I'm going to replace that circle with the module. And so A is a free rank 2Z module with 2 generators, V plus and V minus. And I might see some more than 1 circle, of course. And if I do, I count up how many circles I've got, and I just associate the appropriate tensor product of A with itself. And tensor products are going to appear a lot, so we employ a time-saving shorthand. I simply, if I have a tensor product, I just concatenate the subscripts into one. So for example, this module here, we write down its basis like this. So I'm going to take my cube and make that replacement at every vertex of the cube. I much prefer, the zoom bar is covering my eraser. I much prefer blackboards to tablets, but that copy and paste trick is something that is useful on a tablet, time-saving device. So what's going to happen? Well, here's two circles. So I see a tensor itself. This is one circle. And then I fill the rest of the cube in like this. Okay. So I've just counted up how many circles I have, and I associate the appropriate tensor product of the module A with itself. So now I've turned diagrammatic stuff into algebraic stuff. And if you know anything about Khovanov homology, or you know anything about topological quantum field theories, in a precise sense, what I'm doing is applying a TQFT and turning these one manifolds into these modules. So my claimed aim was to obtain a chain complex. And we can almost see it starting to appear here because of this arrangement of the smoothings in increasing number of ones. I can see that I have 0, 0, the two smoothings with only 1, 1, and then 1, 1. So I'm going to form the chain spaces of this chain complex by just taking these vertical stacks of modules with the same number of ones. And on the far left and the far right, there's no choice here. I can just define this to be C1. So this is the chain complex assigned to the diagram D. I have C1, that's just A tensor itself. And in the middle, I have a choice to make, however, because I see two things, and all I do is I just direct sum them together. So that's what I declare to be my second chain space. And C3 is this module here. So those are the chain spaces, but of course I need the chain maps as well, or rather, sorry, the differential as well, D1 and D2. Where do they come from? Well, if we think about what occurs, or rather, we should notice that I called this a cube, and indeed it is a cube. And we've just been thinking about the vertices, but there's more structure to a cube. There's also the edges. So to find the differential of this chain complex, we're going to use the edges. And if we think about what occurs as we move along an edge of this cube, exactly one entry turns from a 0 to a 1. And we always think about things being oriented left to right. And so one of these resolutions switches from a 0 to a 1. And if you think about that for a few minutes, you'll be able to justify to yourself that the only thing that can happen as I move across an edge is two circles can merge into one circle, or one circle could split into two, and we denote that by delta. And these are the only two possibilities. And so this is a merge map, this is a delta map, merge and delta. If we, sorry, delta and merge. If we refer back to our previous cube. And in the algebraic picture, what does that mean? Well, if two circles are turning into one circle, then this merge map has to be a map from A tensor itself to A. And similarly, along an edge where one circle splits into two, this has to be a map from A to A tensor itself. And in the interest of of time, I'm not going to tell you what M and delta are, but they have a very simple expression. You can write them out formally. And then we can write down what D1 and D2 are as matrices of these maps. And so D1 is the following 2, 1 matrix, and D2 is the following 1, 2 matrix. And there's actually a minus sign appears here. And that's simply formal. There's a very succinct way to add the minus signs. And why do we add minus signs at all? Because we want this to be a chain complex. We want the differential to square to 0. And again, I want to just say the minimum I need to say to get to doubled Khovanov homology. So I'm not going to explain where the minus signs come from. All you need to know is that it's just a simply formal thing to make sure we get a chain complex. And there's another final check that we need to do to make sure that what I claimed is a chain complex really is a chain complex. And before I make that check, I just want to explain one thing that is going to be very important for the next section, or to explaining double Khovanov homology. I said way back at the beginning that Khovanov homology was a bi-graded abelian group. The first grading just comes from the normal homological grading. So elements of the first chain space we declare to be of homological grading 1, and we denote the homological grading by I. We refer to this as the I grading. So here we have 3 of them, 1, 2, and 3. But there's another grading, and it's defined as follows. If you give me an element, and it's either V plus or V minus, we define its J grading to just be plus or minus 1, depending on the plus or minus sign, add the I grading of that element. Okay. And we don't, this isn't enough. We need to also define it for tensor products, because we are seeing tensor products of the module A in our construction, and we simply just extend it over tensor products linearly. So for example, an element of this module here, V++, we just declare that to have I grading 3. We just add up the subscripts. Sorry, we declare that to have J grading of 3. We just add up the subscripts plus whatever the I grading of this element is. So in this case, say this element came from this space, then this has I grading 2. So for example, this one would have J grading 5. But the point to take away is that the J grading is simply the sum of the subscripts, add whatever the I grading is, add wherever the element lives in the homological degree. Okay, so that's something to remember, the fact that this is all bi-graded and there's a J grading. So I have claimed that I can produce a chain complex this way. And I have these 2 differentials. If this CD is going to be a chain complex, then the differential must square to 0. And it turns out that by construction, M and delta must commute as maps. And why is that? Well, if we think about the way we've constructed M and delta, then D2 composed with D1 equaling 0 is equivalent to the condition that running along the top 2 edges and running along the bottom 2 edges also sums to 0. And if we see here, we see merge followed by delta along the top, and along the bottom, we see delta followed by minus merge. So I am going a little bit fast here, just in the interest of time, but the thing to take away is that this commutativity is required for this to be a chain complex. And you can just verify this directly, or in the background, what's happening here is the fact that everything we're doing here is actually a TQFT, and this must be true if you're working with a TQFT. So that shows to us that you give me an oriented link diagram, I can define for you a well-defined chain complex. And then the central point of Khovanov's construction is, if a diagram D1 is related to a diagram D2 by Reidemeister moves, then the homology of the chain complex assigned to D1 is isomorphic to the homology of that assigned to D2. And here we mean isomorphic as bi-graded groups. So in other words, Khovanov proved that this construction yields a link invariant. How did he do it? He simply constructed explicit chain homotopy equivalences between this chain complex and this chain complex, which proves that the homologies are isomorphic. And it's often a subtlety, the fact that they're only isomorphic as opposed to bang on equal. And often we can just ignore that. But there have been some situations in the history of Khovanov homology where it was really important to remember that we only have an isomorphism class as opposed to a group on the nodes. What all of that goes to show is that the homology of the chain complex assigned to this diagram is an oriented link invariant that we denote KHL. And this is what we mean by the Khovanov homology of the link L. So that's the whistle-stop introduction to Khovanov homology. I've given us just what we need to know to move on to the next topic, which the aim of the talk is to explain doubled Khovanov homology. And so we now need to explain virtual links. Again, it's a huge topic, and I'm just going to talk about what I need to get to doubled Khovanov homology. So what's the idea here? Well, virtual links, the study of them was initiated by Kaufman in 1999. And in one sentence, you can describe them as a proper superset of classical links, by which I mean links in the three-sphere. So it's a proper superset of links in the three-sphere defined by adding a new type of crossing. Denoted like this is the so-called virtual crossing. And a virtual link diagram is a knot diagram or a link diagram which has classical crossings, the over and under crossing, but this new third type of crossing, the virtual crossing. Here are some examples. We've introduced a new type of crossing, and it's not surprising to see that there are associated Reidemeister moves to that crossing. And we need to add 4 of them. The first 3 just involve virtual crossings, and they look a lot like the classical Reidemeister moves. And then this 4th one is a little bit more interesting. It involves a mixture, and indeed it's called the mixed move. It allows you to drag virtual crossings over classical ones. The converse is not true, though. If these were classical crossings and this was a virtual crossing, you can't actually drag it across. It's a subtlety. And so we refer to the virtual Reidemeister moves, or rather what we mean by the virtual Reidemeister moves are these 4 moves plus the normal moves of classical knot theory. Okay. And so the quickest way to define virtual links, so the set of virtual links is equal to the set of all virtual link diagrams modulo the virtual Reidemeister moves, just in direct analogy to the classical definition. And this is the definition we'll use for the bulk of the talk. It's purely combinatorial, of course. But I want to say that if there's time at the end, I'll also talk about this topological definition. And it turns out that virtual links are defined by diagrams like this, but they're also defined by in this topological manner as equivalence classes of links in thickened surfaces. So sigma denotes a closed orientable surface of some genus. You take a link inside this three-manifold modulo something called stable equivalence, which allows you to do diffeomorphisms of the three-manifold and certain permitted handle stabilizations. And this world is actually the world I prefer to live in. I spend a lot of my time here. But today I'm going to just describe things using this definition here. So the fact that classical links form a proper subset of virtual links naturally leads to the question, given an invariant of classical links, does it extend to an invariant of virtual links? And the Jones polynomial is an example of an invariant of classical links that naturally and automatically extends to the virtual world. You don't have to do anything. You just employ the Kaufman state sum model of the Jones polynomial. If you give it a virtual diagram, it will give you a virtual link invariant. Khovanov homology categorifies the Jones polynomial, of course. So it's natural to ask if the Jones polynomial extends, what about Khovanov homology? And so this is the main subject of today. How is it possible to extend Khovanov homology to virtual links? So let's just try to repeat the Khovanov construction with a virtual link diagram, and we're just going to ignore the virtual crossings. But I don't really have time today to explain why this is the right thing to do, but it is the right thing to do. When you're first given a virtual link diagram, it's not clear. Maybe you should try and resolve them. Or why are we just ignoring them? And it's because, in a very concrete way, the virtual crossings really aren't there. We have to write them down, but they're really not there. By which I mean, virtual links realize all possible Gauss codes. And in the Gauss code description of a virtual link, the virtual crossing is nowhere to be seen. You don't need to introduce anything. So in a very precise sense, these crossings are phantom. And so we want to ignore them. We don't want to touch them. So let's just try and do that. Let's work with this virtual knot diagram here, which we'll denote by D again. And again, let's try this resolution approach, and we'll make a cube and we'll resolve all the diagrams. Sorry, we'll resolve the diagram in all possible ways. And we immediately see a problem. And that's because along this zoom bar is really nice. Okay. Along these two top edges, we see something that we've already seen. One circle splits into two. And the only difference is that now, instead of having embedded circles in the plane, we just have immersed circles in the plane where they have a self-intersection like this. But still, one circle splits into two, and then along this edge, two circles merge back into one. But along the lower two edges, we see that all we're doing, we're following the rules, we're just changing the resolution at one site, but this time, one circle remains as one circle. This is not possible in the classical case. This cannot happen for classical diagrams. And so we need to address this. More specifically, we see a new type of map required. We denote it by eta, and eta, here one circle is turning into one circle. So in our construction of turning everything into algebra, we must find a new map, eta, which goes from A back to A again. And here, I've written out the module A vertically by its J grading. So the J grading, remember, of V plus was equal to 1. The J grading of V minus was equal to -1. But the J grading contains the I grading. which was basically the number of ones in the resolution. So if I move along an edge, I increase the I grading by 1. I increase the homological grading by 1. So I'll bump up the module in the codomain by 1 in the J grading. So now these two elements, it's still A, but it's been shifted in the J grading, and so its elements are at this grading. And then if we want our choice of eta map to be grading preserving, we see immediately that the only available choice is to set eta to be the 0 map. And again, I don't have too much time to explain why we want it to be grading preserving, but we really, really do. Much of the interesting information contained in Khovanov homology is contained in the J grading. And so if we extended Khovanov homology, but we left the J grading by the wayside, that wouldn't be a satisfactory extension. So given this situation, we're forced to pick the eta map to be the 0 map. But it turns out this causes collateral damage. It breaks the fact that our construction gives us a chain complex. Let's see that specifically. I haven't told you what the form of M and delta is, so you'll have to just trust me. But I want to have a chain complex. I want my differential to square to 0. And that means that running along the top two edges should be the same as running along the bottom two edges multiplied by -1, i.e. this square should anti-commute if I'm going to have a chain complex at the end. But if I start in the left-hand corner and take the element V plus, what do I see? V plus along the bottom two edges must be 0, because eta is the 0 map, of course. But along the top two edges, it's non-zero. And I haven't said what the form of M and delta are, but you'll have to trust me, it really does get you 2V minus instead of 0. So this square fails to anti-commute. And that causes a knock-on effect that you fail to get a chain complex at the end. So you have to fix this somehow. The first option, or there's at least two options, and one of them is you could keep eta as the 0 map, and then apply some new method, new technology to recover a chain complex. Option 2 is you could go further back upstream and alter the construction completely, hoping to find a non-zero and grading preserving eta, and then hope that you get a Weidemeister invariant theory. And option 1 was shown to be viable by Manturov. He produced the first extension of Khovanov homology to virtual links by taking option 1. It was later reformulated by Dijkhuis and Kaufman. And also Daniel Tubenhauer has an extension of Khovanov homology to virtual links that also takes option 1. And kind of mysteriously, it looks very, very similar to the Manturov extension, but it's still open whether or not they're the same. So the takeaway message is that option 1 is viable. It works. You take what you're given, you take eta to be 0, and you fix the chain complex somehow. And just in a few brief words, what the general rule of thumb is, you want to apply diagrammatic technology to be able to find situations like this one where a face fails to anti-commute. And if you're really clever about it, you can detect these things and then you locally set them to 0. You locally fix them. That's the idea with option 1. So that works, it's viable. Is option 2 viable? Well, this is the thrust of today's talk is yes, it is. It does work. So let's denote by A minus 1 the usual module A, but shifted in J grading down by -1. So it still has 2 generators, and I've just shifted their J grading down. And so every time I see a circle now, instead of assigning the module A or tensor products of it, I'm going to assign the module given by A direct sum itself, but shifted down in the J degree. And to give an elucidation here, we'll denote the generators of this module by V upper plus and V upper minus. And they come from the unshifted copy. They're the original terms. So they have the normal J grading. They have 1 and -1. But then there's 2 more generators that come from the shifted copy, and they have J grading 0 and -2. Because all I've done is I've just bumped the J grading down by 1. So this is the module I'm going to be interested in. What does this do? Well, let's go back to the situation with the eta map. If we assign this module to one circle now, then the eta map should be a map from here to here. And again, I've decomposed these modules by their J grading. Here's 0 in the J grading, for example. And remember that if we go along an edge of the cube, the I grading increases by 1. So the J grading contains the I grading, so it gets bumped up too. And so this is the situation we see. This is the what the map must look like. But now, unlike the previous situation, way back here, where all the non-zero elements on the left lined up with zeros on the right, now there's an available non-zero map. And it turns out that there's one choice that works. It's if this is the multiplied by 1, this is multiplied by 2, and this is multiplied by 1. And so this is an available non-zero grading preserving choice of eta. So we've accomplished the partial goal of option 2. We've found a non-zero grading preserving eta. There's still a lot of work to do to show that we have an invariant of virtual links, and I've bundled that all up into this theorem here. You can show that this choice of eta leads to a well-defined chain complex, as in the classical case, which we denote by DC of the diagram D. D here is for doubled, because we've taken the module and doubled it up. And as in the classical case, the isomorphism class of this homology of the chain complex is an invariant of the virtual link, oriented virtual link represented by the diagram, and we denote it by dkh of the link and refer to it as the doubled Khovanov homology of L. So the proof here is very, it follows the same structure as the classical proof. What you have to do, well, first of all, you have to do some quite straightforward checks that you really do have a chain complex. The difficult bit is showing that it's Reidemeister invariant. And as in the classical case, you just directly show that a classical Reidemeister move induces a chain homotopy equivalence. But the interesting fact is that the virtual Reidemeister moves I described before, the purely virtual Reidemeister moves, those 4 moves I showed, it turns out that they actually induce the identity, the simplest possible chain homotopy equivalence. And so if I was, or rather, if somebody had tried to tell me, and I didn't know the history, if somebody had told me that actually Khovanov homology was originally defined for virtual links, I would believe them because it's, or I would have believed them because it's such a nice situation that Khovanov homology just ignores the moves corresponding to virtual crossings, which is exactly what you'd want because the virtual crossings are to be ignored. They're not really there. So it's a very nice situation that it simply just associates the identity. And that's from the combinatorial lens. Through the topological definition of virtual links as equivalent classes of links in thickened surfaces, it turns out actually that these moves are a non-trivial topological operation. They correspond in general to handle additions on a 3-manifold. And so the fact that this construction so naturally incorporates that non-trivial topological operation is interesting to me, and was a pleasant surprise. I thought it was going to be much harder to do this. In any case, to sum up, that choice of eta, by changing the module, finding a non-zero but grading preserving choice of eta, you can directly prove that this produces a well-defined chain complex, which is a virtual link invariant. And here I've depicted the invariant of one such virtual link. The invariant is a finitely generated bi-graded abelian group. And here I've split the generators of that group up by the two gradings, the I grading and the J grading. And if you've seen Khovanov homology before, some of this looks very familiar and some of this looks really weird. This portion here looks familiar. This is what's known as the Knight's move in classical Khovanov homology. So this is a structure that you see a lot when you compute the Khovanov homology of classical links. But this is really strange. This stack of 4 copies of Z on top of itself. This could actually never occur in standard Khovanov homology. So this is a nice example where it retains, and it's kind of indicative of the nature of doubled Khovanov homology. It retains some features of the original theory of original Khovanov homology, but it has many, many strange differences. This Knight's move is very familiar, but this stack of Zs is wacky. So after all of that, what can you do with it? What can you do with doubled Khovanov homology? You can do quite a few things. I'll just outline a couple of them. The first is to say that the theories that I mentioned that take the root of option 1, they actually, in vacuum, they aren't able to detect non-classicality of a virtual link in general, in the sense that they're actually unable to be used on their own to prove that a given virtual link is not classical. In certain situations, for certain restricted classes of link, they can be used for that, but in general, they can't be. But doubled Khovanov homology can be used for this purpose, sometimes. So if the doubled Khovanov homology of a link is not equal to some bi-graded group, direct sum itself shifted down, then that virtual link is not a classical link, it's purely virtual. So this is the one application. It can be used sometimes to detect non-classicality. But the application I'm most interested in is that actually, like its classical counterpart, doubled Khovanov homology contains concordance information also. And in fact, you can extract something called a doubled Rasmussen invariant, generalizing the Rasmussen invariant of classical links. And the amazing situation is that option 1 for extending Khovanov homology and option 2, it turns out you can extract Rasmussen invariants from both of those families of theories. Dye-Kestner-Kaufman reformulated Manturov's extension and extracted a Rasmussen invariant. And in this theory, doubled Khovanov homology also contains a Rasmussen invariant, and very interestingly, they're distinct in general. They're not the same invariant. It's a very nice situation for if you want to study concordance of virtual knots, because you have 2 closely related but distinct invariants to play with. And for example, one can use this invariant to show that the link here that we computed the homology of is not even, it's not a classical link by this fact, and it's not even concordant to a classical link. Now, I know I haven't said what virtual knot concordance is, but for those that know, you can use it to prove this isn't even concordant to a classical link. And I should point out that this wackiness, this weirdness, this stack of 4 Zs on top of itself, this is actually represents the doubled Rasmussen invariant. Okay, so I'm going to finish with a couple of questions that I think are very interesting about the setup. Yeah, so first question, what is the categorical framework of this, this theory? I briefly mentioned way back at the beginning that normal Khovanov homology of classical links is underpinned, well, it just is a TQFT, a topological quantum field theory that takes manifolds to modules and cobordisms between manifolds to maps between modules. But doubled Khovanov homology is not a TQFT. It fails an important axiom of such objects, which are called known as multiplicativity. And it's not even an unoriented TQFT defined by Turayev and Turner. It fails an axiom there as well. Nor is it something called a supervector space. And this is disappointing because a supervector space is one that has 2 levels, and it has a Z mod 2 grading, is the fancy way of saying it. And doubled Khovanov homology looks very much like it could be a supervector space. It has 2 levels sitting on top of itself, but it's not even such an object. So is there some blend or relaxation or some other thing entirely that is a generalization of TQFT? So, you know, there's all sorts of pin, spin, TQFTs. So is doubled Khovanov homology some sort of question mark TQFT, whatever this should be? I think that's a good question. And then finally, I mentioned at the beginning that standard Khovanov homology has very close links and relations to gauge theoretic invariants, to Floer homologies. And it's very interesting to me to try and find out what the relation of doubled Khovanov homology is to such theories. And one tantalizing nugget in a Kornheimer and Movka paper is that they write that they expect the direct sum of Khovanov homology with itself to be related to a particular instanton Floer theory via a spectral sequence. And this looks very much, well, this just really is the doubled Khovanov homology of a classical link. So I think this is a very interesting question to try and get to the bottom of how these things are related. Okay, that's all I want to say. So thank you very much for your attention, and I'll leave it there.
Well, thank you, Will. That's a really interesting talk. Excellent. And wasn't quite expository. It was expository plus, but that's good. And I'm hoping that we're going to have a lot more expository and expository plus talks after Easter. So are there any questions? I noticed that Vasily was putting up questions. I don't know if he wants to.
I was.
Excuse me.
Go ahead, Vasily.
Yeah, I have written some questions on the chat line, so we can look at them and answer.
I mean, do you want an answer?
You should go out of share screen so it's easier to communicate.
Oh, yeah, thank you.
So,
yeah, so
what are your questions, Vasily?
So Vasily asks about the parity projection and how it relates to Khovanov Khovanov homology? Yeah, that's a great question. I don't know. I think that's really interesting. Yeah, I wouldn't. Do you have any guesses? I'm not sure I could even guess. I think it's really interesting, but often Khovanov homology, to work out how it behaves with complicated constructions like that can sometimes be hard.
I'm pretty sure that whenever you say non-classical, you can say not even in the sense that non-orientable virtual, not in the sense that we don't have sourcing structures. So I'm pretty sure that whenever you say that you detect non-classicality, you can prove that you detect much more. That
Right.
it's not, yeah.
Yeah, you're right.
Even about cobordism, I'm pretty sure that, I don't know exactly, but I think that it would not be cobordant to any even link or even not.
Yes, yeah, you're right.
Yes, and I'm quite interested whether we can use other gradings or whatever, parities or whatever homological information for upgrading things in a doubled manner, or we had something in our joint paper.
What do you know about how it behaves under mutation?
I don't know anything about that. That's another great question. I think, well, so this is kind of this relates to the question I put at the end about finding the right categorical framework for it, because most, if not all, the proofs or the work related to mutation and classical Khovanov homology rely heavily on Barnatan's cobordism category. So, for example, I think if I don't want to get the priority wrong, but I think Stefan Verley was the first person to prove mutation invariance of the Z mod 2 theory. And that work is done entirely in Barnatan's cobordism category. But that is completely unknown for doubled Khovanov homology. I have no idea what the right categorical home should be. So yeah, that's a great question, and I think it relates to finding the right categorical framework to put this in, and then you could hope to answer questions like that.
How does it behave under Z equivalence, where that's flanking or crossing with virtual crossings?
It is invariant under such things. Yeah. In Vasily mentioned a joint paper between him and I, and in that paper, there's an upgrade of doubled Khovanov homology, which can detect flanking, but you lose virtual links. You have to stick to links in thickened surfaces.
Mm-hmm.
Is there a Khovanov homology for flat virtuals? Has that been attempted?
No, I haven't put too much time into this, but I thought I had a way to do it, but then it broke. So I don't know.
Actually, I'm very interested in that question. For long flats, we have to Rives maps. For long flat knots, we have to Rives map, which makes our diagram ascending. And having that, we get A states and B states. So we can do something. But I wonder whether we can do something for free knots when we don't have any natural distinction between A states and B states. So yet another question, assume we have just a cube of states, and we know that there are 2 to the n states, but we don't know who is A and who is B. How to define the Khovanov homology in this situation? Maybe without Q gratings, but still, how can we do that?
Yeah, I don't know. I feel like the thing to do is to sort of pick an extra piece of structure. Like I think if you lose, I think basically it's a sort of zero-sum game, and if you lose crossings, if you go from virtual to flat, you lose crossings. So you need to put some extra structure in. So maybe you need to pick a coloring or pick a framing or something, and then you get enough data back, and you can compute something. I think that might be how it should go.
Well, for free knots, we have quite a lot of invariants, and even there are cobordism abstractions, but there is some lack of punctoriality because we don't have Khovanov homology so far. So we don't have a TQFT. We have cobordism abstractions. So of course, everything for flats gives abstractions for virtuals.
Do you
Are there
get
any other questions?
yeah,
or
do you get non-trivial values for closed surfaces in say a 3-manifold cross I?
That's a great question, and I had not ever thought of that. That's a great question.
Well, in fact, whatever pictures we have on surfaces, we can turn them into gratings. So we can draw a cat. So once Khovanov homology is defined, so once differential is set up, it's not hard to decorate it with any homotopical information.
But I think what Scott's referring to is the fact that for classical Khovanov homology,
You don't detect knotting of surfaces. Closed surfaces.
Yeah, if you think of if you take a surface in the four-ball, you can think of it as a cobordism from the unknot to the unknot. You just puncture it twice, and then you get Khovanov homology will give you a number. It'll give you an invariant, but it's always trivial, as Scott says. It doesn't detect knotting. But that's a great question. I'd never thought. Is the same true for this construction? I think, yeah, that's a really interesting thing to ask.
Also, Micah has candidate virtual knots where he can't detect what their concordance classes are. They have a rather large number of crossings, so it's probably very difficult to compute this homology in that case. But it would be interesting to see whether it could attack those few examples.
Yeah, I think that would be interesting. Yeah, unfortunately, I don't have a computer program for double Khovanov homology yet. So
Right.
yeah, it's as you say, it's difficult.
Well, I think perhaps it's time we drew this talk to a close. And many thanks, Will. Nice talk. And we're going to take a break now because it's Easter coming up. And when we start again, I do not know, but I will send around notices about that. We have at least 2 speakers lined up. And if anybody feels they know a subject backwards, or even slightly backwards, perhaps they would like to give an expository talk, that would be great. What do you think, Lou? I think that
certainly would. You also could tell us what expository talks you're interested in. For example, I would love to hear an expository talk about Vaughan Jones' Thompson group and Knott's research. If someone knows that backwards, it would be good to hear it.
Dale, do you know them backwards? No.
I concur, Lou's interest. I'm also interested in Thomson group, and also I'm very interested in how to get how to get four manifold invariants from Khovanov-Rosansky homology. It's really a great topic.
Okay, so thanks again, Will, and we'll meet again sometime in the future to be decided. Okay. So
Will, please send us your slideshow. We'll put it in our Dropbox.
Yeah, we'll do. Okay.
The whole talk has been recorded, and it'll be available on YouTube in the near future. Okay, have a good Easter, everyone.
Thank you.